can we compute the frequencies of the structures? That's the questions. All right, how can we do it? In 1970s, what the structural engineer, they would do this. They would do it. The structural engineer, what they want to do is the input data. That better? No. Can you see it? Is that okay now? All right. So I'm saying, talking about given the input data, this is London force. So we have given London force well, in 1970s. In 1970s, the engineer, what they would do is, given the data, the input data will be sine wave. Will be like a sine, the certain the certain frequencies of sine wave, sine signal. Now, if you look at the frequencies of sine signal to excited structures, if these structures also has the frequencies, the same frequencies as that input frequencies, then what happens? They oscillate, right? So they will do a lot of testing with all different frequencies of the sine wave to excite the structures. That's what they do in the about 1970s. And they have a name called sine sweeping. They got sine sweeping test. Okay, so if they have a sine sweeping test, the sine sweeping test means that I'm going to give the input force, which is a combination of sine signals, with the frequencies giving. And then we look at the output data. If their output data also oscillate with some of the frequencies, we know that that structure has that frequencies. Do you understand what I'm talking about? Do you? No? Yes? All right. So, for any simple structures, it will take a lot of time to do the frequencies ID. I call frequencies ID to identify the frequencies of the structure, because you have to have a lot of frequencies. So in early days, like in 1970 sometime, to test the structure, it might take weeks or months, many months. because they need to do a lot of what we call sine wave, the sine sweeping test to determine the ID. So this class will introduce a very simple and also easy to do testing. There's many methods after 1980s developed without using we call sine sweeping testing. You don't need to do you don't need to do say, okay, I give him certain frequencies and to do the structure. You don't have to do that anymore. So in these slides, you can see that this I call FFT modules. Then we will, in this class, I will also introduce the Fourier, we call the FFT, we call transfer functions. Response FIF, so they call frequency response functions. Frequency response functions. Okay, so that's what we call frequency response functions. So this is a real testing data I show you in this slide. If you look at this, we use the accelerometers to measure accelerations. And there are a total of 162 sensors distributed in these structures. We have 162 outputs. This one, the output here, we have 162 outputs for these structures. We basically install 162 accelerometers in these configurations. Then we do a lot of, we do 3 or 4 called the random shaking input. So instead of the sine signal, then you can use what we call random signals, or random signals to do this. So if you look at this FFT, the FFT modulus, this is the method I'm going to introduce to you, how you compute this is we call FFT modulus, so that you can look at the peak of this curve. Like we have a 1 peak, 2 peaks, 3 peaks, 4 peaks, and so on, 4, 5, 6, many peaks. Each peak represents a frequency. So here we have a frequencies. Here we have another frequencies of the structures. And so at least from this peak you can see we have at least 5 or 6 frequencies that are significant in these structures. Now, if some of these frequencies happen to be also the frequencies of your launch vehicle, then this structure will oscillate with the launch vehicles. This structure may be destroyed or may be broken by the launch vehicles' frequencies. If it happens like that, if this structure is broken during the launching mode, then the structure won't be able to fly anymore. All right. So this is a very important laboratory test. And the test was performed, the whole test was performed in Jet Proportional Laboratory of California Institute of Technologies. So that's the whole structure test in that laboratory. And if you look at this, the top of this slides, there's 3 words called EIA. All right, that's EIA. So that represent the eigensystem realization algorithm. Or EIA. This is the method which was developed in NASA Langley Research Center. That began in 1984. Began to develop this method, particularly to solve for the frequencies of this kind of structures. Now, for any structure, for any structure, what our interest would be the frequency. Okay, is the frequencies. And then another would be the damping. So for any structure, we would like to see what kind of frequencies, what kind of dampings in these structures. And one more important the property is we call Mond shapes. So this, the 3 different properties that we need to compute. In early days, using sun sweeping, we'll be able to look at just the peak of the FFT modules to determine the frequencies, but it's very difficult to compute a damping from that the FFT modules. So frequencies, you can look at the peak of the FFT modules. Well, to be more accurate, we should say that the FIF modules, FIF, frequency advanced function modules. All right. And then, however, the damping, you can, there's some method to compute the damping of each frequencies based on that FRF modules. But those are very approximate computations, not very exact computations. So the EIA, the eigensystem realization algorithm, will be able to compute all 3 at one time simultaneously. That's the message. So if you look at this, although you look at this, if you look, you can compute that one, you can count. Say 1, 2, 3, 4, 5, about 5. The very clear, the very clear peaks, about 5 peaks in these Fi modules. However, if you look at, the computer will be able to look at this FIF and determine there are 22 modes. There are 22 modes. Maybe that means there are supposed to be 22 peaks in that modules. 22. It's not 5, it's not 6. But our eyes, we can see only maybe 5 or 6 or 7 or 8. But computer will be able to see 22. Why? Because some of the peak here, they contain more than one frequencies. In other words, we have multiple frequencies with the same magnitude. We call multiple frequencies. We call repeated frequencies. In other words, these structures may have, we call repeated frequencies. For any one peak, there are more than one frequencies in that one peak. The repeated frequencies means the frequencies of the same amplitude, but they might have a different mode shapes. The frequencies here doesn't mean all distinguished frequencies. They can have repeated frequencies. In other words, we might have a frequencies the same size, but different mode shapes. We'll explain that later when I introduce the EI method. Okay, I think let's take 10 minutes off. Yeah, 10 minutes break. And this is 6 now. So we take 10 minutes break and we'll be back. 因为刚刚那个效果。